take a look at mathematical models, building functions. Just think of all the modeling practice that you had last year, how much that is going to help you. Ah, but you learned. See, that's the catch. Okay, now, example one here. A lot of these things are just situations. How do you go and figure it out? Well, like this one, it says let P be a point on the graph of that. Express the distance from P to the origin as a function of X. Okay. Well, you know the distance formula, yes. So would that be what? Okay. Well, it's going to be on here as well as we continue on. So they go through, set up the distance formula for it. And the nice thing about this is once you got the distance formula taken care of, you can, any value you plug in, it automatically goes and calculates out the distance for it. Okay? Kind of a nice little thing. So a lot of times like this, the modeling stuff that we played with last year, that was simply, convoluted situations where you had to figure out what was going on. Now it's a little bit simpler, but you just have to get into that habit of how do I go and represent that out. Area of a rectangle. This is a fun one. Okay. No, it really isn't. I mean, a rectangle has one quarter in quadrant 1 on the graph. The other one has a third and positive axis and fourth on the positive x-axis. Express the area as a function of x. So let's just take a look at this one here and go through the mechanics of that one. All right. So we've got this drawn out nicely over here, but they want us to express the area of the rectangle as a function of x. Now, that means we're going to put in one number, and that's what we're going to get back out again, right? So, area is simply defined as length times width, right? But we need to be able to assign different value or variables to this for our purposes here. Okay, so this would be simply the x, right? And this would be the y. So in our case here, area is going to be equal to x multiplied by y. That's all fine and dandy. But do I have a way of identifying what y is going to be? Because this point here is going to be moving up and down on this graph. I don't know where it's going to end up at, but it's going to, I circle here once here. Okay. Oh, come on. So either it's going to be sitting here, or it could be sitting up here, or it's going to sit here, but it's always going to be where this is on the line, or on this curve I should say, to dictate what the coordinates of x and y are going to be. So if it is sitting right there, sorry, we're able to identify from that coordinate what our x and y is going to be. So, would I be able to identify what y is based upon x? Well, in this case, we know y is equal to 25 minus x, so we end up having area is going to be equal to x multiplied by, what's y? Well, 25 minus x squared. Yes? So my area actually turns out to be negative x cubed, right? plus 25x. Now, if I want to, I can drop that into the graphing calculator. Clear that out. No, I said clear it out. There we go. So y is going to equal to, let's see, negative x cubed plus 25 graph. That doesn't look so good to us, does it? I gotta fix this, don't I? Did I? I bet you I didn't. I thought I put the x in there. No, the x didn't. The x did not stick. I was going to say that didn't look quite right. There, let's try it again. Okay. Now, does this fit the pattern that we expect? Well, it's a third degree polynomial. It's got a negative on it, so we know that it's been reflected across. So it's coming from the top, goes down, goes back up, comes back down again. But we're talking about area here, correct? So do I care about second, third, and fourth quadrants? No. And do I see all the interesting stuff going on in quadrant 1? No. I see where it's going across the axes, but I don't see where it's got its local maximum. So edit this out. Let's see, I can go to 0. We'll still leave it at 10. We'll leave this set here at 0. And we'll change this out to probably, what, 200? 200? Well, I don't want to play around with this all day, and we know that it came through probably at a 5, so it maxes out somewhere maybe around 2 or 3. If I put 3 in there, what's 3 times 25? What's 3 to the third power? 27. So it looks like it'd be 75 minus 27. So that puts us close to, well, put 100 in there just to make life interesting. And there we go. Graph. Okay, so I see that now. Now, if you're looking at this graph, does it appear to make sense to you if this graph represents the area of that rectangle? Now let's go here and find the max. Okay, left bound. Nope, won't do that. Darn it. So I got the left. The right. Okay. Says the maximum is at 2.8, which comes up to be 48.11. So if x is at 2.8, what is y at? Going back to geometry now, mind you. There is an idea, stated theorem of course, but there is an idea that you're going to get the maximum area on a quadrilateral when it is a well, it is a rectangle, but it's a specific kind of rectangle. Square. Yeah. Yeah, all squares are rectangles, but not all rectangles are squares, so. you're heading down the right path. So if this is going to end up being a square, that means we've identified where things are going to be at, right? Maximum out. However, is that necessarily the case, what we've got here? Because if I look at where 2.8 is, 2.8 goes up to that graph on what? Where does the 2.8 lead to? You put in 2.8, comes up over here, turns out to be there. So this one has to be a rectangle because the formula does not allow for x and y to be exactly the same. It does not allow for a square. Okay. So while a square is going to give us the largest area, in this instance, this is going to give us the largest area being a rectangle. Okay. Now, questions, thoughts, concerns? Wait till the assignment. I know, wait till the assignment. But the idea is, once you know what it's talking about here, you create the formula for it, put it in terms of one variable, and see what you come up with. How is that finding the area of the rectangle? Okay. Well, you recognize that that this peak right here, that's the maximum value for the area, correct? Because that function is simply this from here, correct? Which is our x multiplied by our y. Okay?
So is that line graph?
The actual graph itself that's going here, this is representing the various areas based upon what the width of this is. And the width is dictated by this function. Because once I go past 5, do I even have any rectangles? No. And that's where it falls off and starts going down into the fourth quadrant. So this really only appears in this area or this range where it goes from 0 to 5. So that's what it means when it talks about the domain of A. What numbers can I use for this? Well, if my rectangle is bounded by this constraint of y is equal to 25 minus x squared, okay, I can only put in so many values for this because once I get x squared above 25, or above 5 I should say, it starts going negative. Can area be negative? No, area can't be negative. This function doesn't necessarily work for us. Now, could we go and think of it differently if it kept on going down here? But that means that this would be bounded down this way and going a different way. It changes the shape of the rectangle. Okay? So when I talk about the constraints of it being, on the x and the y axis, and that one corner is always, and it's going to be in quadrant 1, that sets us up for trying to determine where things go. Okay. So, here we go. This is a fun one. Okay. Nice modeling problem here. And you guys thought you were all done with mathematical modeling. Okay. Manufacturer of children's playpens makes a square model that can be opened at one corner and attached at right angles to a wall or perhaps the side of a house. If each side is 3 feet in length, the open configuration doubles the available area in which a child can play from 9 square feet to 18 square feet. Okay, now suppose we place hinges at the outer corner to allow for a configuration like the one shown here. Okay. So instead of the regular old playpen being square like it normally would be, we can detach it, hinges out, so we get that nice little rectangle for the little buggers. Now, it's hinged here. If I pull it out, can I get a larger area for them to play in? Is basically what it's looking for. So, oops, that's not what I wanted it to do. So what we need to do is we need to build a model that expresses the area of the configuration in 66 as a function of the distance x between the two parallel sides. Okay? So, let's start off with this. Now, there are really going to be two different components of this. Right? Because here we said we had, this is the x value. Okay? And this is going to be our y, so to speak, if you want to go and put it in that term, right? Because area is going to be equal to, okay, we'll just do x times y. Okay. Start off very basic. Now, if I go and take a look at this rectangular area that is identified over here by this, is x always the same? In 66, is x always going to be the same? Not in 65. No, it could change, right? Depending upon how far you pull out that peak, right? Is y always going to change? Because if we say that y is this, it's going to be 3, right? So that never changes, does it? So what we want to consider here is not necessarily the y there, or this here, but that we are always going to have the x multiplied by 3, correct? Will that always provide us the area of the rectangle? Okay. Because right down here, 3 plus 3 is 6, correct? That gives us our y. 6 times 3 is 18, so that does that. So for the area of the rectangle, it is simply going to have to be, well, 3x. Let's rewrite that so that we have it the way we want it. Okay. Now, what about the triangular part? So we've got this piece that's here. Okay. Now, if I want to find the area of that triangle, what would the area of the triangle be? Well, how do we find the area of a triangle? Okay, base times height divided by 2, correct. That's for every triangle. So we get our base, which happens to be x, multiplied by the height divided by 2, correct? So now, do we have an idea of how to create the area of this thing? I don't know. Well, if x is 6, the height would have to be 0, would it not? If x is 6, the height would have to be 0, because it comes back down to this configuration here.
Oh, wait, it is a right triangle.
Yeah. So when you take a look at what's going on in this piece of it right here, you end up seeing that you've got your height over here.
Oh, I know, I was.
Okay, and this is over here. But now take a look at how that height goes. Do we have to consider that it's also 3, or can we just consider the triangle by itself? It's always going to be 3 plus h if I wanted to hold in the whole thing. But if I'm talking about just this triangular piece here, do I have to consider the whole thing for the height? Right, you're right. You see, what I'm trying to get at here is, you see the dotted line there? Some people go, oh, that's the whole height there. It's not. Break it to be this distance. Let's see, come on. X has to be this distance right here, okay?
But we don't use all of that, we only use half of it, it's half of that, and then the little, that line.
Oh, I understand what you're saying now, but then again, don't I have two of those triangles? So I'd have to multiply by two. Yeah, do it all as one piece, that's why I'm talking about X. For this triangle here, X is the base, the height is H.
So if you go one, it's 3 times the height.
Yeah.
It'd be half of X.
No. Okay,
If you got one triangle, it would be half of X.
why would I want to figure out half of that triangle? Wouldn't I want to figure out the whole triangle to begin with?
I know it, and then you figure that out and then multiply by 2.
But why would I want to divide X by half, figure it out, and then multiply by 2? Why wouldn't I just keep it in terms of X? But X isn't 3. Because if X is 3, H is 0.
X is 6. X keeps changing.
But X keeps changing. As you keep pulling this piece out, this distance here has to collapse, has to shorten up.
I didn't know that changed. I thought it was just George. I thought it was just one like this.
Well, if you think about this mathematically, you got a 3 here and a 3 there.
Let's throw on some. No, I didn't. Okay, I didn't know.
Okay. Break out
I know
the
what
old.
you mean.
Yeah, because now, this is the length of it, right? And as this comes out, where do the ends of the yardsticks go? They get closer together, okay? But now my height increases out here so that I have an area to work.
Yeah, I thought it was like a chest with more doors.
Okay, but yeah, but if the doors open up there, then the little bugger can get out.
That's what I was. I didn't.
Ah,
I thought it was a door.
okay, that's fine, no. And that's part of it, you gotta sit there and analyze what the situation is. This is why we had modeling last year. And, what is the problem? What is the situation? So sometimes you have to create a physical idea or representation of what you've got there so you can actually figure it out. Okay. So now, the area has to be expressed as a function of X, correct? It says build a model that expresses the area of the configuration shown in 66 as a function of the distance between the two parallel lines, right? So, now my next question is, do I have that? Do I have that piece of information built? Do I have enough information so that if I plug in X, I can get my area? Okay, so now we gotta sit there and play and figure out the height, correct? Because the height has to be in terms of what? What does the height have to be listed in terms of? Okay, when we're talking about the area being identified in terms of X, that means that I put in something for X and I will be able to get out the area. Okay? Now what I need is to figure out, we got the area of the rectangular part, we've got the area of the triangular part. Now how in the world am I going to figure out what this is? So if I just put in X.
Depending on what the.
Right, but how do I write that mathematically?
So if you crumple it up.
No, you cannot crumple it up and throw away.
Just stand it out.
How do I get a representation. Now, you were going down a road before that we said wasn't so good when it came to calculating the area of the triangle, correct? Now, if we go down that road that you were on before, and just think of it in terms of a right triangle, can I use a right triangle to represent the height, or to help us represent the height? Your neck hurts. Well, you can move. Okay. Representations again. I got a triangle here. I need to come up with a way of identifying this is the height and this is x. Okay? And this is always going to be what? 3. Now, is this relationship always going to be there? If this is a right triangle, what do we know about it? Yes? That'll get us an area. What else do we know about this?
Oh, h squared plus x squared equals
Bingo. So if I've got h squared plus x, but now this x isn't the full across, is it? It's half x, so it's got to be x over 2 squared is going to be equal to 3 squared. Now, can I rewrite this such that x turns out to be the number that I can put in and get out the height, so that h, the height, is dependent upon x? Can I do that? Can I get down to that point? So I can get h. Can I solve for h? So h squared turns out to be 9 minus x squared over 4. Would you agree with that? Okay. So that means that I end up with, let's see here. Yeah. So now, I'm going to do something to this that you guys might not really think that I should do. See this squared bit in here? I've got perfect squares in here. So if I could rearrange this so that when I take the square root of it, I can pull that out, that would really be helpful. So, I'm going to say that h squared is going to be equal to 36 minus x squared over 4. Multiplied by 4, got a common denominator, added them together. So now, when I go and take my h is equal to the square root of 36 minus h squared over 4, I can rewrite it as h is equal to 1/2. Okay? And no, I can't go and do anything with the rest because it's addition in there, or subtraction. 36 minus x squared. I'm stuck at that point. I cannot go any further. Okay? Because I had the 4 here, the square root of 4 is 2. So I was able to pull the 2 out. Okay? Yeah. Does that make sense now? Okay, so now I was able to rewrite h in terms of x. So when I get back to that triangle now, so that I'm looking at where I got h here, and I've got x going all the way across in 3 and 3. So the area now for this thing turns out to be base times height divided by 2. What's the base? Base is x. What's the height? The height turns out to be 1/2 of the square root of 36 minus x squared. All over what? All over 2. It's a triangle. Of course it's going to be 2. All over 2. Okay? So now, can we do some simplifying on this? can't do. Yeah, because there's a subtraction going on within here. Okay. Then it would be this, subtraction is the same thing as addition, just going the opposite way. Addition or subtraction, you know, you're adding the opposite. No, you see, what you're doing is you're looking at like factoring. Okay? Because if you wanted to factor that out, you'd have to factor it out so that, because this would factor the difference of two squares. It would not factor out into something squared. Okay. It'd be 6 minus x times 6 plus x. And because those are two different things, you can't go and take the square root of that and say, hey, that's what it's going to be. Okay. But if you like, I could go and take this 2 and put it over 1, right? Is that legal? So I can take this up over here and I can multiply it by its reciprocal. So area is going to be equal to, yeah. See, that's why I put 2 over 1, so that instead of dividing by a fraction, I'm multiplying by its reciprocal. So if I multiply by its reciprocal, what does that give me? That's all multiplied up here, correct? There you go. So that means that area is going to be equal to actually 1/4, but we're going to write it like this. X over 4 square root of 36 minus x squared. Oops, sorry. I could keep it divided by 2, but we want to try and simplify things as much as we possibly can. Okay? That's as simple as it gets. Well, part of the reason why we always want to make sure it's simplified, I'll put it back into technology. Like when we're doing our app coding, this function down here, the last one that we've got, is going to take up by far less space than the one above it. You got to remember, everything that you put in there is going to take up memory. It's going to be size. And if I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 versus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I've saved myself a little space. Now, we've got this little bit of information, okay? We are going to need to have that all the way back up here. Okay? So we said our area before was x times h divided by 2. Now I've been able to put in h in terms of x. So what we end up with here is going to be the following. Takes a little bit. But this is going to get added with, now we're going to put this in here for that, and we end up with x squared. Okay? It's going to get multiplied by h. X times, this is over 4, again, then we end up with, we end up with the square root of 36 minus x squared, and guess what this is all over now? 2. Okay? So we're going to end up having to do some more simplifying down for this whole formula. So what we end up with is one formula that rules them all. No? So area is going to be equal to, this ends up getting combined together, so we'll end up having, and this is going to get multiplied through here by the 2, so we'll end up with 3x plus x squared over 8 square root of 36 minus x squared. Okay? that's all, actually, that just took care of A,
Oh my god.
okay? Now the rest of it's real simple, find the domain of A. Well, what's the domain of the area? The smallest area that it can be is 0, the largest area that it can be is 18, right? Maybe, maybe not. But we would be able to take this function, put it into the graphing calculator, find its maximum, and we can go from there.
What day is it? Is that Wednesday?
Today is Wednesday.
Oh crap.
So,
I was like, we still have like 2 minutes.
no, we're out of here in a minute. So, there you go. It'll give you a head start on the problems, and on Monday,
Yeah.
we'll be able to talk more.